So, we look over here, what's coming up. Don't forget you have vocab due tomorrow. I saw a handful of you have already done that. Thank you very much. Hopefully you have already completed homework 0. I will be posting homework 1 and that should be due on Thursday. Mason.
Okay.
Yeah, it's like the same thing. Yeah. So, I honestly try to grade that as fast as possible. It is mostly for you. It is just a very small percentage of your grade, but it is to encourage you to both take a look at the vocabulary and also have a list of words that are helpful to know. So, yeah, upload that onto Canvas. Okay, remember that when I give a due date, it is at midnight, and so that's why it's usually the day before class. We will have our first quiz on Friday because I'll have to be at a conference, so I'm sorry it's coming up really quick. But as a way of giving you a little bit of help, what I will do is I will allow you to use your notes on this quiz, not all quizzes, okay? But on this quiz, you can use your notes, and that should encourage you to try and take good notes. I will instruct the person who is giving the quiz that you are not allowed to use laptops or phones or tablets or whatever. So if that's how you keep your notes, you'll need to print them out if you want to use them. Okay. Questions about any of that stuff? All right, those of you interested in SHPEP and PEP and UK Med, remember those due dates are coming up like this weekend or next week or something. So be paying attention to those things. Okay, yes, Chip. Yes, yes. So anytime I give a quiz, anything covered prior to that day is fair game. If I cover something only in class that day, the only way I would put it on the quiz would be a bonus point. Okay. But on this Friday, the only thing you're going to be doing is the quiz, which I tried to time those to be about 20 minutes. Sometimes people are like, I'm going to take every spare second. And if I give them a whole hour, they will take a whole hour and you will have the whole hour if that's what you want. But I aim for them to be the majority of people done in 20 minutes. Okay, so just some quick reminders of where we were. We talked about atomic radius. This is really the driving force of a lot of our periodic trends, is that size matters because size determines how close are the electrons, the outermost electrons. What do we call those outermost electrons? Valence. The valence electrons, how close are they to the nucleus? So size really is a determining factor for everything. Remember that our trends go along on the diagonal from the upper right down to the lower left or reverse. So in this case, the smallest ones are up helium. Helium is the teeny tiniest. And francium, if we could measure it, that's one of those that like, there's probably at any given moment only 3 francium atoms in existence. So we can't really measure it, but we would assume that it would be larger. I have given you this chart that kind of shows you those trends. You're welcome to put that with your notes. I'm likely to give you a handful of elements and say which one of these is the largest. You basically just need to remember the trend. And we can see that there are some exceptions. So remember here in the transition metals, there's some things that are off. So this isn't 100% true, but for our purposes, I won't ask you about exceptions in size. So size, it's just, where is it on the periodic table? That's the only thing you need to think about. Then we talked about ionization energy. Open that up. Okay. So we have our definition here of ionization energy that we're just taking an electron away. And then we can see from the chart that the lowest ionization energy is for group 1. That's connected back to size because that electron is farthest away. And the highest ionization energy is in group 18. And that's because those are the smallest ones. Okay, so sometimes I will use an analogy of a parent with kids. The nucleus is the parent, the kids are the electrons. If you're like fluorine, you're a parent who the kids are not allowed outside of the house, even to play in the yard. They must be where I can see them at all times. Those kids are not getting kidnapped, right? Like mom always knows where they are. She maybe has a leash on them, right? But if you're like lithium, lithium's like, go, explore, take your bike, go down to the creek, play in the quarry, have fun, just be home by dark. All right. Those electrons can go everywhere. But then that's one, this is like a kid in this scenario that, easier for that kid to get hit by a car or to be, take off with his friends and disappear or to get kidnapped or something. So those electrons are lost in that sense much easier. So ionization energy. All right, now if we think about, I don't think we looked at this graph, but if we think about how we do our orbital diagrams from last fall, remember our bottom is the 1s, and then we do the layers going up. Okay, each layer has sublevels. Okay, so this is layer 2. These are sublevels. This one's a little bit lower than this one, but they are both in the same layer. So we call all of these valence electrons, not just the ones that are at the very highest, even the S get to be part of that valence because they're all part of that 2 layer. Okay. Our ionization energy is from whatever level that layer is to the top, because the top represents having pulled the electron so far away that it can't feel the pull of the nucleus. It's like positive charge over here, negative over here, and the negative is like, I can't tell there's positive charge anywhere. Okay, that's how far away they are. So this is the ionization energy. So how far up or down those lines are tells us how big this gap is. So we're going to look at diagrams like this for some of the different elements and talking about some of these trends. Ionization energy is a little trickier than the radius because there are exceptions. And so we're going to talk about those exceptions. All right, so we can see on the graph that I gave you, this one, and also over here, the exception. So generally the trend is going lithium to neon, it goes up, but here I have a little bit of a downhill, and here I have a little bit of a downhill, okay? I have the same thing in the next row, boop, boop, and then over in here. Now we're ignoring transition metal for right now, but we've got a little boop there. This one, it isn't going downhill, but it's still not quite as high as you would expect. So those are exceptions, and that's what we're going to talk about. All right, but we saw trend was as we move across from left to right, the ionization increases. As we go down, it decreases. So it is the opposite of size. All right. So I'm going to skip this set of slides and look at exceptions. Okay. So we said the exception was pretty consistently when we go from the second to the third. So the third element should be higher than the second, but it is not. It goes down. Okay. The sixth element should be higher significantly, and it either goes down or it goes very slightly up instead of way up. So those are 2 exceptions. So in the third element, we are changing from the S block to the P block. So the first 2 are called the S block because we have S electrons. This over here, over to the last row, that's the P block. So when we switch which type of orbital we have, we get an exception, okay? The sixth one is going to be because of pairing. So I'll describe that in more detail in just a second. So you need to know where those exceptions are. Now, as a general rule, if I ask you about ionization energy and the elements are not right next to each other, just follow the general trend. So if I was looking at boron versus fluorine, they're not right next to each other. I'm just going to follow the general trend. Fluorine should be higher than boron. But if they're right next to each other, then I have to ask myself, is one of the elements either in 3 or 6? And if they are, then I have to think a little bit harder. All right. So let's look at that first exception. The third element, boron or aluminum, that whole column has a lower ionization energy than the second. So the trend is it should be higher as we go across, but in this case, it's lower. Why does that happen? It's because we're ionizing from a different orbit. So, let me put this back so you can see what to write down for a second. This says that p orbital is less stable. In chemistry, less stable means higher in energy. So further up on the page, because that's where we're drawing our energy. And the higher it is on the page, the smaller the gap between there and that zero mark at the top. So there's less energy needed to ionize. All right, so now let's compare beryllium and boron. So beryllium is are in column 2, boron is in column 3. Now in reality, all of these lines would be just a little bit lower, maybe like, you know, a third of the way down. It'd be a little bit lower, but they wouldn't be way low, okay? So beryllium has how many electrons? 4. So we would have 1, 2, 3, 4. We would fill up the 1s and the 2s, right? So when we're ionizing, we are ionizing from that 2s position. But with boron, we have 1 more electron. We have 5 electrons. And remember, our ionization goes from wherever that last electron is, that valence position, to the top. So the difference between boron in the top and beryllium in the top, the difference there is smaller for boron than it is for beryllium. And that's because the electron's coming from a p orbital instead of an s orbital. Right? Now they're pretty close in energy, but there's a little bit of a difference. And so that's why we see that change. If I'm comparing 1 versus 2, notice this gap is bigger. And it would actually be a lot bigger than what I'm illustrating here. Go ahead and put it on the page. All right, so when I take that electron away, my ionization is that becoming boron plus. All right, so this is our full diagram. Now we're going to go across from boron over to neon and see what happens to these orbitals as we are processing across. So as we increase the number of protons, all of the orbitals get a little bit lower in energy. And so since they're getting lower in energy, the electron coming out of carbon has a little bit further to go, so the ionization energy is high, right? And that trend's going to continue for nitrogen. Okay, a little bit more energy, but now we're going to hit our next exception. Okay, so nitrogen is in column 5, oxygen is in column 6. Okay, so here's oxygen. So we kind of think of it like this: the energy is lower. Why wouldn't we have a bigger ionization energy? Because those 2 electrons are in the same orbital, they're right next to each other, and they're negative. And what do 2 negative things want to do with each other? They want to repel, right? And so part of that repulsion is, I don't want to share my bedroom with you. I want to kick you out of my bedroom, right? So this is what we call pairing energy. So that electron is a little bit higher in energy, right? So it's still basically there, but we can think of it as being just a little bit up, okay? Since it is a little bit higher in energy, and this is where the higher and lower kind of gets a little bit convoluted in our brains. Since this one is further up, the ionization energy from here to the top is less, okay? So oxygen has a lower ionization energy than nitrogen. Okay, so that's one of our exceptions. Now, why wouldn't that apply to our other ones, our other elements in the same row? Well, it does. We still have pairing energy with fluorine, but remember, all the electrons are sinking down in energy. So the difference between how much fluorine has sunk down and that pairing energy, is the sinking down makes more of a difference by the time you've done it for fluorine than the pairing energy does. And so now we're just back onto our regular trend. Same thing for neon. All right. Now, the reason this is a periodic trend, the reason we don't keep getting a greater ionization energy when we go to our next element, so neon is 10, for our 11th element, instead of the electron coming from here, the p orbital, for nitrogen, not nitrogen, sodium, it is coming from way up here in the 3s. So we can see this zigzag line is the difference between where it was for neon and where it's coming from for sodium. So we have a really big gap. Okay, so this is what creates the periodic trend. And our exceptions come because we're either switching from the S to the P or because we've got pairing energy. All right. So within the same row, whatever element is further to the right is going to have a higher ionization energy as long as they're not right next to each other. So if I compare carbon and fluorine, which one has a higher ionization energy? Which one's further right? Fluorine is further right, so it has a higher ionization energy. What about beryllium over here versus neon? Which one has a higher ionization energy? Neon, it's much further to the right. You can kind of see that on this chart. Blurred out, but here's beryllium and here's neon, way higher over there. So as long as they're not right next to each other, you're just looking which one's further right. But if they are right next to each other, you got to remember the third one is less than the second one, and the sixth one is less than the fifth. So we looked at the second row. In the third row, those would be aluminum and magnesium. So aluminum's a little bit less than magnesium, and sulfur's a little bit less than phosphorus. Now the trend in the sixth row doesn't continue to be the sixth being less as you go further down. It's just not as much high. But when I ask questions, I'll ask about the first, second, third row. Try not to confuse. Okay. So that's ionization energy when we're talking about just removing one electron, but we can have +2, +3, +4 cations. So we can have multiple ionization energy.